Let's discuss this theorem. See, in this theorem, we have a matrix space XD. In this diagram, I have shown that thing. Y dy is a subspace of a matrix space XD and AVN is subset of Y. So with the help of this basic information, we have to prove two statements. So out of that, these two, only one statement I have written here. First, we will prove this one. After that, we will go for the next statement. Okay. So see, what is the statement says? X is the limit point of A in Y if and only if X is the limit point of A in X. So that means there is some point X. Okay. If it is a limit point of A in Y, okay, in subspace Y, if and only if it is a limit point of A in matrix space X. If and only if is there, that means we have to prove in both ways. So out of that, I will start with the first. That means I am going to consider X is a limit point of A in Y. That thing I have written and I have to prove the second statement. Okay. So what is the given information? X is the limit point of A in Y. So you are familiar with the definition of limit point. So let us use the definition of limit point. So therefore, for every r greater than 0, bxr minus singleton x intersection A is not equal to phi. Okay. So see, it is a limit point in subspace Y. So we should take open ball in a subspace Y only. So you know well how to express open ball in Y. So that is nothing but open ball in X, right, intersection Y. See, in previous video, we have discussed one theorem related to that. We have proved this thing. Okay, so that's why I am writing it directly. So intersection Y we can take outside. Okay, so therefore what can we write? Remaining things I am writing as it is. Bxr minus singleton x intersection A intersection Y not equal to phi for every r greater than 0. So A and Y, if you take their intersection, obviously we will have A. So because A is subset of Y, so therefore if you take their intersection, obviously it is A. So I am replacing A intersection Y by A. So therefore, see, what can we write? Bxr minus singleton x intersection A is not equal to phi for all r greater than 0. This is the definition of limit point. Getting? And we have a ball in entire matrix space X. So that's why it is a limit point in X. So therefore we can write, therefore X is a limit point of A in X. So we started with it is a limit point of A in Y. We proved that X is a limit point of A in X. So after that we have to prove in the reverse way. Okay. So first make a screenshot of it. Then we'll go for remaining part of this theorem. So let us discuss its converse part. So now I have assumed X is a limit point of A in X. And we have to prove X is a limit point of A in Y. So let us start with the given information. I am simply using the definition of limit point. So therefore, for every r greater than 0, bxr minus singleton x intersection A is not equal to phi. Okay. See, I am doing in the reverse way exactly. But A is subset of Y. Agree? A is subset of Y. So therefore, A is equal to A intersection Y. Getting? So if you take intersection of A and Y, obviously we will have A because A is subset of Y. So that's why I can replace A by A intersection Y here. So therefore, bxr minus singleton x intersection A intersection Y not equal to phi. Okay, and this is true for all r greater than 0. So I replace A by A intersection Y. After that, what will I do? I will take this Y inside the bracket. Doesn't matter. It logically it will have the same meaning. Getting? So therefore, bxr intersection Y minus singleton x intersection A is not equal to phi for all r greater than 0. So you know that any open ball in X intersection Y means open ball in Y. So therefore I can replace it by, so therefore this is nothing but open ball in y, by xr minus singleton x intersection A is not equal to 5 for all are greater than 0. This is definition of limit point. So therefore x is a limit point of A, but this ball is in y, so that's why x is a limit point of A in y. So therefore x is a limit point of A in y. Okay, so in this way we proved this statement. After that we will go for second part of this theorem. So let us discuss second sub-question. So in a second sub-question we have to prove a very simple thing. If you know that A bar denotes a closure of A in X, then we have to prove that A bar intersection Y is a closure of A in Y. This thing we have to prove. Okay, so see, let us start its proof. I have written some basic things. A bar is a closure of A. Okay, A bar is a closure of A in X. So this is a given information. And what we have to prove, if you take intersection of A bar with Y, then we get closure of A in Y. This thing we have to prove. Okay. So I am assuming B is a closure of A in Y. We have to prove A bar intersection Y is a closure of A in Y, but I am assuming B is closure of A in Y. So finally what we have to prove? We have to prove B is equal to A bar intersection Y, then we can declare yes, A bar intersection Y is a closure of A in Y. Okay, so let us start with this thing. B is a closure of A in Y. So you know that closure is always a closed set. We have proved this thing. A bar is always closed set. So this is a closure. A bar means closure. Closure is always a closed set. So therefore, B is closed in Y. So we know that every closed set in Y can be expressed, okay, as a intersection of some closed set in X with Y. So therefore, B is closed in Y implies B is equal to F intersection Y, where F is a closed set in X containing A. Okay, so it is a closed set in Y, so that's why we can write B is equal to F intersection Y, where F is closed in X, right? And a very important thing, that set F contains A, that is very important thing here. Very important thing, A is subset of F. After that, what will I do? I will take bar on both sides, closure of both sides. So therefore, we will have A bar subset of F bar. Okay, we have some space, so let us continue here. So implies A bar subset of F, because F is closed set, right? F is closed set, you know that. F is closed set, so therefore F bar is equal to F since it is closed. So I will take intersection with Y on both sides. So A bar intersection Y subset of F intersection Y. So this implies A bar intersection Y subset of F intersection Y. We have seen somewhere. Yes, F intersection Y is nothing but B. So this is equal. This is subset of B. So I will call it as equation statement number 1. This is very important thing. So we proved that this is subset of B. Now we will prove that B is also subset of this one. Then we can say both of them are equal and we can declare A bar intersection Y is a closure of A in Y. Okay. So now what is our target? Our target is to prove B is subset of this one. Okay. There is no more space. So I suggest you to make a screenshot of it. Then we will go further. So let us prove the second half. So here, what is the information we have? A bar is a closure of A in X. Okay, A bar is a closure of A in X. We have already proved closure is a closed set which contains set A. So therefore, A bar is a closed set in X containing A. So see, if I take intersection of A bar with Y, then is a closed set in Y. Closed set in Y containing A. So we have a very simple technique. If you have any closed set in X, if you take its intersection with Y, we will have a closed set in Y. So same technique I use. It is a closed set in X. So if I take its intersection with Y, we will have a closed set in Y. and which is this set contains A, right? So see, but what we have assumed, B is closure of A in Y. This thing we have assumed it is a closure of A in Y. So therefore, B is a smallest closed set in Y containing A. So this is one property of closure, containing A. This is one property of closure. See, both of them have the same property. This is also a closed set in Y containing A. This is also a closed set in Y containing A, but this is the smallest. This is the smallest, so that's why B is subset of this one. So therefore, B is subset of A bar intersection Y. I will call it as 2. See, in statement 1 we say this is subset of this. In statement 2 we say B is subset of that one. So that means from 1 and 2 we can combine and we can say both of them are equal. So therefore, from 1 and 2, B is equal to A bar intersection Y. What is our B? B is a closure of A in Y. So B is nothing but that one. So that's why we can declare this is also closure of A in Y. So therefore, A bar intersection Y is a closure of A in Y. So in this way we proved, yes, A bar intersection Y is a closure of A in Y. So make a screenshot of it. After that we will stop. Thank you. Bye bye.